Hello, we are moving on to listing and talking about the idiosyncrasies of all the types of contact forces. We had discussed the non-contact force due to gravity, mg. But now we're moving on the types of contact force and also net force. We're also going to be practicing creating force diagrams, all right? And as well as using those force diagrams and applying Newton's second law to create equations. If you haven't done the reading, please do so. Please do your Coleto reading or OpenStax if you're using either book. And it's probably time to get started on your homework if you haven't even started on it yet. Okay? All right, well, let's talk about the first one. Let's talk about tension. So tension is a term used by physicists to talk about ropes and strings, okay, and rubber bands too. But suffice it to say is that a rope is basically just linked up atoms. A rope or a string is just linked up atoms, and so this molecular bond of those atoms are what is being referred to as tension here, okay? And it's also important to point out that tension ropes will pull in both directions. It's important, this is very important to know, that despite whatever direction the object is moving, in this case it's a safe, if the safe was moving up or down, no matter what, a rope is always going to be pulling an object. You don't attach, if you go rock climbing, you don't attach a rope to a person and then start pushing the rope up against the person. That's really weird. But really the main thing is that tension is just kind of a conceptual term, but really all it is it's referring to the rope, and ropes will always pull, they never push. Okay? So let's do a problem. So here we are, we have a problem where we have a rock that is being lowered, but it's speeding up as it's being lowered, okay? So, given that this rock is speeding up as it's being lowered, what can you say about the rope tension? Is the rope tension greater than the object's weight? Is the rope tension less than the equal to the object's weight? Is the rope tension less than the object's weight? Is the rope tension can't be compared to the object's weight? So which one of these choices do you believe is true? And please pause the video and make a selection. All right, well, what I'm going to do is I'm going to mark up this document like I always do in these videos, and let's try it out. So what I'm going to do is I'm going to create a free body diagram. So I'm going to draw a dot, okay, and then I'm going to draw a coordinate system, okay. And it's just going to be a typical x direction, y direction coordinate system. Positive x is to the right, negative x is to the left, negative y is down, and positive y is up. All right. What I'm also going to do is, actually, negative x, or positive x, I should say. All right. What I'm also going to do is, I'm going to go ahead and let's go ahead and make a list. Now that we have this set up, let's make a list of what forces are acting on this object. Okay, so we have a rope, we have a rock being lowered at a constant velocity. Okay, now let's talk about the non-contact force. So essentially, what you're going to get used to is that all objects have mass. All right, unless you're talking about photons or something like that, which is much later on in physics. But when we're doing force diagrams, all objects have a mass, and then they're probably going to be in a gravitational field like the Earth. In this case, this is supposed to take place on the Earth, so this rope is lowering this rock down, as it's speeding up. Okay? And so that means the Earth is down here pulling on it. So essentially the Earth is acting on the object. So one force is going to be the non-contact force due to gravity. Okay? And it is going to be working in the downward direction. Now that we've got the non-contact force due to the weight of the rock out of the way, let's talk about what is physically touching the rock. Well, there's only one thing touching the rock, is the rope, which is going to be a tension. And ropes only pull, and the rope is attached to the top of the rock, so it's going to be acting upwards. It's not on the ground. The rope is not on the ground, so there's no normal force or friction force. There's no springs or anything else working on it. It's just the tension of the rope and mass times gravity, so G, down. Okay? All right, well, let's go ahead and list those out. I'm going to list out the weight of the rock is, and let me use blue for that. And I'm going to list it as blue, and that'll be negative mass of the rock times gravity. Okay? And then I'm going to write the vector for the tension force. So the rope is pulling it up, and I'm going to give that a green vector. That's a green vector, and the border is green. So that'll be working up. And I don't know about the proportions just yet. I'm going to worry about that later. And I'm going to put that, and since it's a rope and it's pulling, it's going to be pulling it upwards. And I've got to label that green. And there we go. Now those are our two forces acting on it. There's no other forces acting on it. What I also like to do is I like to draw the velocity vectors and acceleration vectors off to the side. Do not attach velocity vectors and acceleration vectors to the force diagram. So it says the object is moving down, so it's got a velocity vector that is negative, and it's also accelerating as it's moving down, because it's speeding up as it's moving, as it's being lowered. Okay. Now we're building up to answering the question here. Okay. So now let's sum the forces in the y direction. Okay. Let's do that. Well, you have a tension upward. You have a mass times gravity downwards, and with force, when you create this stuff, after you do that, you apply Newton's second law. So after you've accounted for all the forces acting on your object, which is the rock in this case, you then, it was tension up, mass times gravity down, put the vectors on these guys. I should have done that. I apologize. So there's vectors on every one of these little things here. All right. Well, now that I've done that, then you set it equal to mass times acceleration. Well, it's accelerating in the negative direction, so this is actually going to be a negative mass times acceleration, right? Mass cannot be negative. That negative comes from the acceleration, right? So after summing up your forces, you set it equal to mass times acceleration, but leave a little space because you might need to tag on a plus or a minus to your mass times acceleration, as in this case, it's a negative acceleration. Well, now let's compare tension to weight. I'm going to bring weight onto the other side. So tension is, I'm going to add that to both sides, is going to be equal to mass times gravity, but you have that acceleration that's negative ma there. So let's take a look at this equation and think about it for a second. If it wasn't accelerating, tension would be equal to mass times gravity. So the rope's tension would be equal to that. But that is not the case. It is accelerating in this case. So it can't be equal, the tension of the rope can't be equal to the object's weight. Well, is this proportion right here, mg minus ma, greater than mg, or is it less than mg? Well, mg is the weight of the object, but you're subtracting off a number. So that means mg minus ma is less than mg, right? Which means this, the tension is going to be less than mg, because the tension is equal to the weight of the object, but minus this amount. So that means the tension has to be less than the object's weight, which is c. All right? So when you're given these abstract kind of weird questions, what I want you to do is I want you to pause. I want you to draw a center of mass, draw a coordinate system, and label your coordinate system. Okay? Then what I want you to do is I want you to list out the forces that are working on it. Tension, springs, friction, normal force, weight. And then I want you to think about the directions that they're working on. Okay? And then go ahead and put those vectors in. Then I want you to draw the velocity vectors and acceleration vectors off to the side. And then use this to shape your sum of forces stuff. We didn't sum the forces in the x direction, by the way, because there are no x direction forces, right? That's just 0 is equal to mass times acceleration in the x direction. By the way, this is y direction. I should have subscripted that, right? So there is no acceleration in the x direction. So after you do all this, then you basically create an equation where now you could actually think about this particular context in reference to these conclusions. So that's what I want to get you used to doing. But also I wanted to illustrate how ropes work. So even though this rope is moving down and it's accelerating as it's moving down, it's actually speeding up as it's moving down, the rope is still pulling up on it, right? If you're the rock, you're going to feel a rope pulling you up a little bit. It's going to provide a little bit of a resistance, right? It's not in free fall. So you didn't just chuck the rock and the rope off the side of the building, right? So there was a little bit of resistance, so the rope would be sliding through somebody's hands way above here. So the rock would feel a little bit of a pull of the rope upwards. Okay? So this is kind of how tension works. It's basically an abstract term for a rope or a string. And the ropes pull. Ropes will always pull. Okay? Well, now let's talk about the normal force, right? So the normal force, just like a rope, is just a bunch of linked together atoms, right? And so really, it in a way is kind of an electric force because it's linked together atoms holding bound together. And in this case, this surface or this table right here is actually kind of, they're showing it bending a little bit, right? If a really heavy person sat on a table, wouldn't you see that table kind of bend and strain to hold that person up, right? So in this case, this weight, the weight of this object is being supported by these atoms, right? Well, normal, what they mean by normal, they don't mean like normal versus abnormal. They mean like perpendicular, right? And so this normal force is always going to be perpendicular to the surface, no matter what you're talking about, okay? And here we have a person, and also, actually, I should back up for a second. The term surface is actually interpretable too, right? A wall is a surface, but, we've been talking about the floor being a surface, which has a normal and is holding up her weight. But in this case, the wall is actually another type of normal, which is equal to the force of her push against the wall, right? It's the force of the wall against her push, right? So if she's pushing against the wall is going to be pushing back against her. So, and in a way, you could call that a normal force, right? it's just equal to her push, while this normal force would be equal to her mass times gravity pointed down, right? This one would just be, this person's got a center of mass right around their navel, so that would be mass times gravity down, which would be then equal to their weight up, right? Sum the forces in the y direction. Actually, I should delete this mass times gravity down, and let me show you what I'm talking about. They have a normal force up, they have an mg down, right? And so when we sum the forces in the y direction, right here, normal force minus mg, and if the person is not accelerating in the y direction at all, then that means their mass times acceleration in the y direction is 0, and then that means n minus mg is equal to 0. And then in this case, as long as this person is not accelerating up or down, the normal force, the ground, is actually just holding them up. Over here, you sum the forces up in the x direction. Okay. Basically, the normal force here is just the push of her hand against the wall, right? The force of her hand against the wall. So by doing the same method. But the point is, a normal force is perpendicular, and that's why they call it the normal force. It's perpendicular to the surface. And the term surface could mean a wall, it could mean the ground, or it could even mean the ceiling. If her hand was against the ceiling up here, you'd have a normal force working straight down. Okay. It's really only the force of the ground that could possibly be equal to the weight of the object. But there are some cases where the normal force is not equal to the weight of the object. In this case it is, because she's not accelerating up or down. All right. So let's talk about when the normal force is not equal to the weight of the object. Okay. Well, actually equal to the weight of the object to begin with, right? So if you just have an object just sitting on the ground and it has no acceleration in the y direction, that would be a case, and the ground is, it's just sitting on the surface and has no acceleration in the y direction. This would be a case where the normal force is equal to mg, right? You sum the forces in the y direction, normal force minus mg. Here's the free body diagram. Normal force minus mg is equal to may, and the acceleration in the y direction is 0, so that is 0. So then normal force is equal to mg, right? But there are cases when the normal force is not equal to mg. So let's talk about it. We talked about riding an elevator and how you have inertia, and that how you feel heavier or lighter or equal to your weight when you're riding an elevator back in 2 activities ago in 2.0. But let's talk about why that is. And we're going to use free body diagrams to do it. Okay, so here you are, you're in an elevator and it's at rest. And then and you're standing on a weight scale. And then the elevator begins to speed up as it's moving upwards. So the elevator is going to be speeding up with a positive velocity as it's accelerating upwards as well. All right. And so the question is what is the weight scale going to be reading as you are speeding up, as you're moving upwards? Will you feel heavier or lighter or the same weight that you normally do? All right. Well, let's don't answer that question just yet. Let's go ahead and do a free body diagram. We're going to do a free body diagram on this person. Okay. And then I'm going to go ahead and I'm going to draw my coordinate system on this person. Positive x to the right, negative x to the left, positive y upwards, negative y downwards. Okay, and let's go ahead and list off what forces are touching this person. Well, actually, what forces are acting on this person? Well, the person is going to have a weight, so they're going to have the non-contact force due to the earth pulling them, and that'll be in the downward direction. Okay. And then now we only have to figure out what is physically touching the object. Well, the person is only standing on the weight scale. And so in a way, that is going to be a normal force, and that is going to be acting upwards. Okay. Or you could call this the weight scale too. It's the same thing. But really what it is, it's the bottom of the elevator. So it is a normal force. Okay. All right. Well, let's draw those out now. And I am going to do the arrow thing. And I'm going to draw, actually let's draw the normal for it. Let's draw the weight of the person first. And so here we have the weight of the person is going to be down. And we're going to label that negative mg. And we're going to call it blue. And there you go. So I'm just translating my list of forces to this force diagram. And there you go, there's the first one. This next one is the only other force, it's normal force, and that vector should be pointed upwards. And I don't know if they're the same size or are different sizes, but I'm just going to put a vector upwards. And then we'll worry about if they're the same size or different sizes, whether the normal force is greater than, less than, or equal to the weight of the object. Okay, so that vector is upwards. And so this is going to be a positive normal force. And that is going to be green, and that is pointed upwards. All right. Well, now I've got those, and I probably should just be on the safe side. I'm going to put vector heads on those guys, on everything that is a vector. All right. So now I have my settings for an equation. So we're going to apply Newton's second law in the y direction. The x direction, Newton's second law is just 0 newtons, and that's equal to mass times acceleration in the x direction, which is 0. So there is no acceleration in the x direction. There's only an acceleration vector in the y direction. So we only need to really sum the forces in the y direction. So I'm going to have a normal force pointed up. I have an mg vector pointed down. And now that I've accounted for all of my up and down vectors, I'm going to set it equal to mass times acceleration in the y direction. And that is positive, because that acceleration vector is upwards. Right? So now let's talk about it. So the reading on the weight scale, I maintain that a weight scale only measures your normal force. Okay? It does not measure your weight. If you are standing on a weight scale on the ground, right here in this case, if this was a weight scale right here, it would be measuring your weight. However, if you're standing on a weight scale in an elevator, it is not going to be measuring your weight. Not all the time. If you are accelerating up or down, it will be measuring only something other than that. Its reading will not be equal to mg. In this case, the normal force, I'm going to add mg to both sides, is actually measuring, the weight scale is actually reading your weight, but it's also going to be reading your acceleration as well. Okay? So the normal force, so the weight scale is going to be measuring your weight, but also your acceleration in this context too. Which means your normal force is going to be reading your weight plus your acceleration, which is basically going to show you having a heavier weight. That tells you that a weight scale measures the normal force, and it doesn't measure your weight. It only measures the normal force. Okay? So this is a case of this. All right? Cool. Well, there's another case in which the normal force does not measure when the normal force is not equal to mg. And that's when an object is on an inclined plane. And we talked about, when we did vector addition stuff, about inclined plane and tilting a coordinate system. Okay? So here we have an object sitting on an inclined plane. Okay? All right? And we want to create an equation for the measurement of the normal force. So again, what we're going to do is draw a dot. So this box is being held in place by a rope. It is not moving. So it's got a velocity of 0 and an acceleration of 0. It's not moving. All right. So we're going to do a force diagram, but in this case, basically a rule of thumb is you always want the coordinate system to be you want the x direction axis to always be parallel to the surface. Most of the time, I would have to say like 99% of the time, you want the x direction of the coordinate system to be parallel to the surface that you're on. Okay? So in this case, x direction is going to be parallel to the surface. So that means positive x is going to be down the plane. The negative x is going to be up the plane. Positive y is always perpendicular to the positive x. So positive y is going to be actually kind of pointed at this tilt. And negative y is going to be pointed down that way. Okay? We'll do more of inclined plane stuff later on, but I just wanted to show you this. Okay? So now that I have my coordinate system here, let's talk about this object now. This object has, it's got mass times gravity down. Actually, I'm going to use black to list these off. Mass times gravity is always pointed straight down to the bottom of the page. The normal force is going to be pointed in the positive y direction. I'm going to actually now be using and down means down bottom of the page. The normal force is going to be pointed up, parallel to the surface, so in the positive y direction. The rope is pulling it, so the tension in the rope is pulling it in the negative x direction. There is no friction or anything else acting on it. So here we go. All right, cool. Well, let's start drawing this. I'm actually just going to use a pen and I'm going to color it. mg is going to be pointed straight down. Towards the bottom of the paper, bottom of the page. mg is always pointed straight down to the bottom of the page. The normal force, which is green, is going to be pointed up along the y-axis, right here. And that's the normal force, is pointed in the positive y direction, so I'm going to put a positive there. Notice that I did not give mg a label. And that's because it's a diagonal to this coordinate system. I'm going to have to break mg up into up and down and left and right. Okay. The tension in the rope, I'm going to use black, and that is pointed to the left. Okay, and that's pointed in the negative x direction. All right. Now this y direction, this mg force, has to be broken up for the coordinate system. Okay? So what we're going to have to do is we're going to have to break this up into up and down and left and right. So basically I'm going to have to use this angle theta to help me with that. Okay? And what you're going to find out is that angle theta is this angle theta right here. And how did I get that? Okay, well, here you go. You have you have a plane right here. You have an inclined plane. Okay. And this is theta. And this is going to be 90 minus theta up here. Okay. Well, what I'm going to do is use a different color for what I'm about to do. I'm going to create a smaller system right here. I'm just going to cut this in half. And even though it looks like it's smaller, but this is still going to be 90 minus theta right here. Correct? Well, now if I draw another line through this right here, perpendicular to the surface, this is going to be 90 degrees, and this is also going to be 90 degrees, right? But we said that this red guy is going to be 90 minus theta, so that means this must be theta right there. Okay, and so that's how we get this to be theta right here. This is theta right there. Okay. We'll go more into this when we do the activity on inclined planes. The point of this is this. This mg vector pointing down is actually going to be, that's going to be the hypotenuse. Okay, and this is going to be pointed in the negative y direction, which is negative mg cosine of theta, and it's also going to be pointed down the plane as mg in the positive x direction, positive mg sine of theta. Okay, and so you could see when we sum our forces in the y direction right here, which is all we need to do on this, that n is not equal to mg. It's actually equal to n minus mg cosine of theta. And since it's not accelerating in the y direction at all, that is 0. So what you find out, if it's on an inclined plane, cosine of theta, your weight scale, the weight of the object is not the normal force here, it's mg cosine of theta. It's less than your weight. So that normal force here is going to be greater than, is actually the weight of the object is going to be greater than the normal force, because the normal force is equal to mg cosine of theta. Okay. So another way real quick to lose weight, other than riding up and down in an elevator, is to put your weight scale on an inclined plane, and it will be measuring a lower weight for you. And you'll look weird standing on it. All right. That's the two ways in which normal force is not equal to the weight of the object. Suffice it to say, if the object is on a normal coordinate system, as up and down and left and right, positive x, positive y, negative y. So the mg vector is pointing in the negative y direction, and also it's not accelerating up or down. Well, then the normal force will be equal to the weight. Okay, but if you are accelerating up or down, the normal force will not be equal to your weight. And if the object is on an inclined plane, the normal force will not be equal to the weight. It will be less than the weight of the object. Okay? Well, since we talked about the surface force of normal force, we have to talk about friction, because a surface creates two forces. It creates a perpendicular force, which is the normal force, but it also creates a parallel force, which is friction. Okay, so friction is a resistive force. Okay, if an object is being pulled to the right, friction is going to resist that pull. So in essence, friction is a resistive force. So Okay, so it's a resistive force, and it's resistive to the direction of motion. Right? But friction itself is dependent on a couple different things, right? It's dependent on, so right now we'll talk about those. So first of all, it's dependent on how sticky the two surfaces are, right? So if you have a shoe, the bottom of your shoe, this is your shoe, right here, it's a green shoe, and this is the ground. Your shoe will be trying to bind to the ground. So if your shoe was really sticky and the ground was really sticky, well, they're going to bind together really well. The atoms are going to bind together really well. So there's that mutual stickiness of the two surfaces. If one surface is smooth and the other surface is sticky, it's going to bind okay. If both of them are smooth, they're not going to bind. They're going to be really slick and very smooth and not bind very well at all. But if both surfaces are really sticky, the bottom of the shoe and the top of the ground, the bottom of the shoe and the top of the ground, so this space in between them is this space right here. Well, that means they're going to bind together really well, and you're going to have an even more resistive force to the direction of your motion, to the direction of your velocity vector. Okay? So it's also kind of a strange thing too, in that when you are moving forward to the right, okay, so in order for you to move forward, you've got to actually, so let's say you want to move forward to the right. Well, your foot gets bound to the floor, and if your foot, that's what is actually propelling you forward, right? If your foot was to slip, it would slip to the left. It would slip to the left. Well, that means the frictional force is going to be pushing you to the right. Essentially, the frictional force is pushing you to the right because your foot is being bound to the floor, and you're applying a force of your push, right? So this is the force of the push right here. And if your foot was to slip, it would be slipping to the left. Well, the frictional force would be opposite the direction of that slip. Or if your foot was sliding, it would be sliding to the left. Your frictional force would be pushing you to the right. So the point is that this is a resistive force. Your foot actually wants to go to the left because you're pushing to the left, which then the frictional force is propelling you to the right. So it's really weird. It's counterintuitive to what you think, right? And the other weird thing too is that there are two types of frictional forces. When your foot is on the ground, really your feet, if you put your big toe on the ground, your big toe stays at this position relative to the ground, and doesn't move until you lift it back up, right? Unless your foot slips, and then your foot would be moving to the left. That is called a static friction force. So a static friction force is F sub S, okay, and is actually due to this coefficient of static friction, which is mu sub S. So the static friction force is actually mu sub S times the normal force, okay? That means the object is not moving, right? So if you've ever done sled pushes, if you worked out, you've ever done sled pushes and you had to get that sled, you put 400 pounds on it, you begin to push it, and to get it to even start moving, you have to push it really, really hard. But once it's moving, well, now that sled has kinetic friction, which is mu sub k. By the way, mu, right there, that's the Greek letter M, and it's the Greek letter for kitty cat. It is not the Greek letter for kitty cat. I'm just using that to help you remember that's mu. Kitty cat. Anyways, so there's two types of frictional forces. There's a static friction force when the object is not moving, and you have to break that to get it to move. Now, once it is moving, now it has a vector. And so when we're talking about a static friction force in reference to a velocity vector, which way your foot would want to slip should it then break static friction. And then that frictional force would be opposite that direction. If you're sliding to the right, if you're moving to the right, a kinetic friction vector will resist the direction of that motion to the left. Okay? So there are two types of friction vectors, and static friction and kinetic friction. Now, it's kind of interesting because I told you that once you are pushing sleds and you get them to start moving, well, now it's much easier to keep pushing them. That resistive force of the kinetic friction is a lot easier than the static friction. Okay? Well, this kind of confirms it, right? So when you have two surfaces, so over here they're talking about two different materials, glass on glass, aluminum on aluminum, rubber on concrete, steel on aluminum. So they're talking about two different types of surfaces. And here they have the static friction listed for each surface. And then they have a kinetic friction listed for each surface. So there's a couple things you might notice here. Compare each object's static friction to each object's kinetic friction. And what you might find in that in almost all of the cases, the static friction is almost always greater than the kinetic friction. There are some cases where the static friction here and here is equal to the kinetic friction. Okay. Oh, and also here, and I'm not sure about the lubricated ball bearings. They're almost zero. So, but in every other case, you'll have static friction greater than kinetic friction. And this is a unitless number. It's just a coefficient. It's a comparison of stickiness of surfaces, or really it's like the binding of these two surfaces, right? So that's that one component of friction. Okay, and so you could see in which case which object has the largest static friction as well as kinetic friction. Well, weirdly enough, if you have an aluminum object sitting on an aluminum floor or aluminum surface, they are weirdly strong in their binding to each other. I don't think of aluminum as a slick surface. I don't think of them as a sticky surface, right? I think of aluminum as smooth. Like I think of it like a can of Pepsi or something like that. So I'm not sure if they're talking about polished aluminum here, but if it is polished aluminum, well, I think it doesn't have any polish on it. That usually when you polish something, you put like a film on it. But if you have just aluminum, bare aluminum, and it's just been polished down and you haven't put a surface on top of that polish, it's just aluminum but smooth aluminum, I think that's what they're talking about in this case, that they bind together the most, right? And in fact, the static friction in this case is what is it? It's 1/3, no, it's 1/4. It's almost 1/4. It's a little bit over 1/4 greater than the kinetic friction. Well, let's talk about that other component of friction. Besides the stickiness of the surface, which is the coefficient part, there's the normal force. Okay. Well, why isn't the weight of the object? Okay. Well, again, if an object is accelerating up or down, the contact between the object and the surface is not going to be dependent on the weight of the object, right? It's actually going to be defined as the normal force, really. So the friction, since friction is basically a result of a surface, it should take into account also the connection between the force between the surface and the object. In this case it's going to be the normal force, right? And in the last thing that we did, right over here, the connection between the normal force and the surface on this inclined plane was mg cosine of theta. It wasn't the weight of the object, right? And in this case, the connection between the surface and the object here was not equal to the weight of the person. It was actually greater than the weight of the person. Okay, so if you think about it, if you put your hand on your table right now, put your hand on your table, and just limply put it there. Don't put your whole arm down on it. Just barely put your hand on the table, and then pull your hand towards you across the table, and feel how easy that is to pull. Now what I want you to do is put your hand on the table and push down really hard on it and pull your hand towards you. It should be more difficult, right? So you haven't increased the weight of your hand when you've done that. All you did is add the force on top of that, which was increasing the normal force, which then increased the friction, the resistive force of your pull, right? So friction has a few things it takes into account. It takes into account the stickiness of the surfaces, whether they're not moving or they are moving, as well as the normal force. And so that is what friction is. It takes into account all three of those things. All right. So here we go. We have Sanjay pushing a refrigerator across the kitchen floor, and it is speeding up. The amount of friction between the amount of friction between the refrigerator and the floor is less than Sanjay's push, equal to Sanjay's push, or more than Sanjay's push. So is that friction force, as Sanjay is pushing it to the right, speeding up, is that friction force less than Sanjay's push, equal to Sanjay's push, or more than Sanjay's push? Go ahead and pause the video and try the problem. All right, well, let's try it out. Again, I'm not going to try to answer the question. What I'm going to do is I'm going to draw the velocity. It's speeding up as it's moving to the right. So I'm going to draw the acceleration vectors and velocity vectors off to the side. Now to do this problem, what I'm going to do is I'm going to draw my dot, and then I'm going to draw my coordinate system. Okay, and again, you've got up and down and left and right. I want to make sure the x-axis is parallel to the surface. And then I want to label my coordinate system. All right. So once I've got that labeled, now what I'm going to do is I'm going to list off I'm going to do a force diagram on the crate, not on Sanjay, but on the crate. Okay. So I'm going to list off what forces are working on the object. Well, the crate has a mass times gravity. I always do the non-contact first, and it's pointing in the negative y direction. So it's pointing straight down towards the bottom of the page. Sanjay is pushing it. So this is the force of Sanjay on the crate. That looks like it's going to be to the right. He's pushing it to the right, so that'll be in the positive x direction. I'm going to put vector heads on those guys there. It looks like the normal force, which is going to be pointed in the positive y direction, since the ground is here, it's pointed up and it's not tilted or anything. And friction. Well, this guy is moving, so it's a kinetic friction, not static. If it had a velocity of 0, it would not be moving. It would be static, not kinetic. But in this case, it does have a velocity vector, so it is moving. So that's kinetic. and want to draw a better K. And since the object is moving to the right, because Sanjay is pushing it to the right, this vector is going to be pointed to the left. All right. Okay, here we go. So I've listed out all the forces, listed out the non-contact force, and also it's got 3 contact forces acting on it. Let's do it. I'm going to just draw those freehand. mg is down, and that is down. Normal force is up, so it's positive normal force in the positive y direction. Sanjay is pushing the crate to the right, so Sanjay on the crate, and that'll be in the positive x direction. And friction is in the negative x direction, and that's a kinetic friction. Okay? Well, now, since we have forces in all directions, okay, we're going to have to sum up the forces both in the x and y directions. Okay? In the x direction, I have a negative friction force, and I have a positive Sanjay force working on the crate, and that's equal to mass times acceleration in the x direction, and that is in the positive direction. Okay? In the y direction, I have a normal force up, and I have a weight vector down, and that's equal to mass times acceleration in the y direction. Well, it's only accelerating, it's only increasing speed in the x direction. It means the y direction acceleration is 0, which means normal force minus mg is equal to 0, which means normal force is equal to mg. Okay. Well, friction force is equal to negative mu sub k times the normal force, and that's equal to Sanjay's push equal to mass times acceleration in the x direction. So I'm going to bring this component onto the other side. I'm bringing the frictional force onto the other side, and that's equal to the friction force, which is now positive, times the normal force, plus mass times acceleration in the x direction, which, if I plug in this part right here, the friction force can be rewritten to be, we don't need this part to answer the question, as mg. It's not accelerating up or down, so, and it's on a level plane, that's coordinate system is correct. So we could actually rewrite it like this. But what we really need is to compare the force of Sanjay's push to the friction force. But the friction force, okay, if you look at it, Sanjay is pushing this friction force, and since we brought it on the other side, Sanjay's push is equal to the friction force plus the acceleration of the crate, which means that Sanjay's push is greater than the friction force, which is mu sub k times the normal force, which is equal to mg in this case. So that's what we can conclude, which is that means the friction force is less than Sanjay's push. All right, pretty cool. So that's kind of what is listed here. They just, in this problem, they're talking about the object actually does have a push, and here's a friction force, so this matches up with what we did right here. Okay, so that's what this slide is for. Let's talk about springs. Okay, a spring is an interesting force because springs can push or pull an object. Okay, an example of a spring pushing an object, if you've ever seen underneath the front end of a car, there's that big spring that's holding basically up the car as part of the stabilizer system. And that's a spring that solely holds up the engine and holds up the front end of the car. So that's a spring that is a resistive spring that is a pushing spring. Okay. You've also probably had springs like slinkies where when they're collapsed, they're up against each other. So when you pull them, that slinky is going to be pulling against you. Okay. So what do these pushing springs and pulling springs have in common? Well, actually, all springs, if you think about it, want to get back to its equilibrium position. So it's called a restoring force, right? The spring is a restoring force, and they want to get back to what this is an equilibrium position, right? So if you have a spring when it's fully relaxed, nothing is working on it, it's just right like this, it's just lazy on the ground. But if you pull that spring past its equilibrium position, well, now it's going to want to snap back. It's going to apply a force to snap back. Force of a spring is F sub S. It'll want to pull itself back to that equilibrium position where it was fully relaxed. If you then push this spring in past its equilibrium position, it's going to want to push back against you so that it goes back to its equilibrium position. So a spring always wants to get back to its equilibrium position, okay? And that spring and that force is going to try to restore it to its equilibrium position. If a stretched spring is going to pull, stretched. A stretched spring is going to want to pull. A compressed spring is going to want to push. Okay? So just remember that a spring wants to get back to its relaxed equilibrium position, and it's going to either pull or push you to get back to that. All right? So the equation for a spring, which is Hooke's law, is equal to the spring constant K times delta x, which is x final. It's its end position minus beginning position, and this beginning position can be the relaxed position. Usually this is in reference to the equilibrium position right here. So in a way, this is a position-based force, right? The spring constant is how stiff the spring is. So this is actually spring stiffness. And this is in the spring constant. It's not like friction where it has it's not a coefficient. It actually does have a value to it, and it's a Newton per meter. Okay. So the spring constant is how stiff the spring is. So if you have a stiff spring, it's going to really resist. If you pull it, it's going to really pull you hard back. Or if you push it, it's going to really push back against you really hard. Okay. And not only that, the further you pull a spring, so if you have a spring right here, it's at the equilibrium position, nothing's going to happen. But if you pull this spring really far, you pull it a little bit, x, versus 2x, well, that spring force is going to increase, right? So the spring force is equal to k delta x, right? Well, if you've increased that distance 2r, well, if that delta x has gone up, well, that's going to increase the spring force, right? Okay. And also, if you've increased how stiff the spring is, that's going to really increase the spring force. Okay. So there are two things that you have to consider when you're talking about springs, is how stiff the spring is, and then how far past the equilibrium position the spring has been pulled or pushed. And again, a compressed spring will push, a stretched spring will pull. Okay, and that's essentially what we're saying right here. Well, let's do a problem. You've got a box that it's a 2 kilogram box. Okay. And you've compressed it. Okay. So you've pushed it in. It must be want to be down here. So it's been compressed in this distance x. Okay. So this is x equals 0. Actually, do this. It wants to be here, and now it's here. So this is x, and this is x equals 0. So this is x naught. So it wants to be here, but it's here. Okay. So you've compressed it, and now you've let it go. And now it's going to be speeding up as it's moving down. And they want you to create a free body diagram right here using this, and then sum the forces in the x and y direction. That's it. You don't have to solve for anything. Okay? So go ahead and try this out on your own and see what you come up with, and let's see what kind of equation you get here for your free body diagram. Try to use the steps that I showed you, and go ahead and pause the video and try it out now. Okay, we're back. Well, we've got our dot written for us, so I'm going to draw the coordinate system right here. Y direction, negative y is down, positive y is up. X direction, positive x is to the right, negative x is to the left. All right. All right, let's go ahead and let's list out what forces are acting on our object here. Well, our 2 kilogram object, it's going to have, I'm going to list it out. I'll list it out up here. It's going to have a weight vector directed in the negative y direction. And so once I have my non-contact force listed, what else is physically touching this object? Well, it's a spring, and it's a compressed spring. So it's a force due to a spring, and it's compressed, which means it's going to be pushing it down, which is going to be in the negative y direction as well. All right. There's nothing else touching it. Correct? Yeah, nothing else touching it. Got it. All right. Well, I am going to go ahead and I'm going to draw the weight vector. The weight vector is mg, and it's going to be pointed down, so I'm going to actually give it a direction too. Okay. And now I'm going to draw the spring force. I'm going to use black for the spring force, and I'm going to just give it a downward force. I'm not sure about its proportion, but it's also pointed straight down, and it's the spring force as well. And so it's a negative F sub s. All right. Well, I think we've got that complete. There doesn't seem to be any other forces that we have listed here or over here. Okay. Well, let's try this now. There are no forces in the x direction. So mass times acceleration in the x direction is 0, and there are no forces in the x direction. It is accelerating and moving in the y direction. So we're going to have a negative m sub g minus f sub s, which, by the way, is just equal to k delta x. In this case, k delta y. Okay. Which I'm actually just going to list that here. It's k delta y. And I should have made sure, since this is in the y direction, we want to be consistent. So this is y sub 0 is equal to 0. All right. And this is the k. And here's our vector on that force. And that's equal to negative, the acceleration is down, negative mass times acceleration. So there we go. That looks good. That looks pretty straightforward to me. So you're supposed to learn from this that it's a compressed spring and it's going to push, okay, and it's going to be pushing down in this case, all right, and that also we're just reviewing again force free body diagrams and how to apply Newton's second law in Newton's second law to our equations and create equations. Well, let's do another one. Here we go. We have a 4 kilogram box attached to a spring and then released. Okay, so it looks like, and they said it's a stretched spring and then released. So let's just do this. It's got its equilibrium position is right here, and it's been stretched to here. Okay, and it's a 4 kilogram, and then when they said it was initially stretched, and now it's accelerating, initially stretched at a distance of 0.5 meters, and it accelerates at 2 meters per second. Okay, so that means it's going to be accelerating to the left so it's going to have a negative x direction acceleration, and I'm going to actually say it's speeding up as it's moving in the x direction. Started from rest. So it's speeding up as it's moving to the left. All right. So it's a 4 kilogram box attached to a spring and then released. It's got friction, so there is friction working on this object. So that's a mu sub k, and it's kinetic friction. That means it has a velocity vector. And it was initially stretched this distance, so this delta x. So this is going to be delta x, and its delta x is going to be equal to 0.5 meters. And it's accelerating to the left at negative 2 meters per second squared. All right. And they want to know what the spring constant is. So we have to find out what is k equal to. Well, go ahead and pause the video, and given those notes, go ahead and attempt this and solve for k. Try it out. All right, well, we're back. Well, let's go ahead and do our coordinate system, and then we're going to list out all the forces that we know are acting on this object. So our coordinate system is going to be this. It's going to be up and down and left and right. And it is going to have forces in the left and the right. Positive x is to the right, negative x is to the left, negative y is down, positive y is up. All right, that looks pretty good. Let's go ahead and list out all the forces acting on this. So mg is going to be pointed down. All right, and that's our non-contact force. Now we just have to think of what is touching this object now. And this is a 4 kilogram object. Well, what's physically touching it? A spring, and it's a stretched spring, so it's going to be pulling, and that means the spring force is going to be pulling it to the left. So that k delta x is going to be pulling it in the negative x direction. It's a stretched spring, so it'll be pulling it to the left. Now you have a surface. The surface is going to be acting in the positive y direction as a normal force, but since the object is moving, and it's going to be moving to the left, the frictional force, which is mu sub k times the normal force, is going to be working to the right. So that is going to be in the positive x direction. The object's moving to the left, and friction is a resistive force, is going to be working to the right. All right. Well, let's go ahead and start drawing. Well, I have weight working down. So that's negative mg is pointed down. So I've got that guy right here. Now let's draw orange. Actually, use baby blue for our spring force. So spring force is going to be acting in the negative x direction. And it's just really easy in this case, since it's just k delta x, just use k delta x. All right. And then give it that, label it. Let's use green. The normal force is pointed up, and it'll be in the positive y direction. So I got that. Oops, I forgot to use baby blue to knock out that other guy. There. And now we've got friction. For some reason I think friction is red. So friction is going to be equal to positive mu sub k times the normal force. All right. And our force is right there. All right, so I've got vector heads on everything. Cool. Cool, cool, cool. And I just got that one, took care of that. So I've got all of my forces listed. All right. All right, got my force diagram written. Sorry about that interruption. Okay, well, let's sum the forces up in the x direction first, and then apply Newton's second law. So you have a negative k delta x to the right, to the left, I should say, and that's got a vector head on it. And then you have the friction force, which is to the right. So I'm just looking here. When I was summing the forces up in the x direction, I was just looking at the equations here. Okay, and I see only two vectors, one pointed to the left, one pointed to the right, and I'm just copying down what I've labeled them as. Okay, and it will be accelerating to the left, so that'll be negative ma sub x. All right. So always, once you've accounted for all your vectors, set it equal to mass times acceleration. And then subscript it as x or y. That's like that's putting like a period at the end of a sentence. Okay. Y direction. I've got a normal force up. I've got an mg vector down. And that is going to be equal to mass times acceleration in the y direction, but I have no acceleration in the y direction, so I'm drawing that line through there. All right. Well, we need to solve for the spring constant. The first thing I'm going to do is, since we have a normal force here, I'm going to be solving for k. I don't know what the normal force is, so I need to get that first. So normal force minus mg equals 0. So basically that means normal force is equal to mg. All right. Now I'm going to copy this down. Negative u sub k times delta x. Delta x is going to be 0.5 meters. We're going to be solving for k, plus mu sub k times normal force. Normal force in this case is equal to mg, and that's equal to negative mass times acceleration in the x direction. I'm going to solve for k. So negative k delta x is going to be equal to negative ma x. And I'm going to subtract this to both sides, negative mu sub k mg. And since everything's negative, you can just multiply through by -1 and make everything positive if you want, which I'm going to do that. And then to isolate k, it's k times delta x. I'm going to divide it both sides by delta x. And what I get is, I'm going to get max plus mu sub k mg over delta x. Okay. Well, now I'm going to put in our numbers. This is going to be 4 kilograms and that's times the acceleration, which is 2 meters per second. We're just, since we've already listed the negative here, we're just putting in the magnitude. Plus mu sub k, so that mu sub k is 0.2. 0.2. The mass again is 4 kilograms. And gravity is 9.8 meters per second squared. It's not negative 9.8 meters per second. It's just got a magnitude of 9.8. We took care of the magnitude over here. Delta x is 0.5 meters. So this is going to work out to, k is going to be equal to, let me put all these numbers into a calculator. So this is going to be 8. So I'm going to go 8. So 4 times 2 is going to be 8. So I'm going to go plus, now I'm going to go 0.2 times 4 times 9.8, in parentheses, enter, 15.84 is a result of this whole top part, and I'm going to divide that by 0.5, 31.68. So this is a huge spring constant. Typically they're close to 1, so this must be a huge spring, really thick spring. Let me rewrite that a little bit better. 31.68, and that'll be a Newton there. This is a Newton, so this is a Newton per meter, and that is our answer. Okay, well this concludes forces 2.2, and I hope you learned a lot about all those different contact forces. Okay. And also how to write force diagrams and then put them into equations and then solve for something. Okay? All right. Have a nice day. Bye.